This video discusses what we talked about in class on October 3rd, 2023 with atom orbital hybridization. Hopefully you should all be familiar with the fact that orbitals in atoms, the s, p, and d, can sometimes combine to make a hybrid orbital, hence the name orbital hybridization. We want to know, for this to get started, that an s orbital has one pair, i.e. one thing in this case. A p orbital has three pairs, or three things. And a d orbital has 5 pairs, or 5 things. So if I have something listed like an sp orbital, like this, I want you to imagine there's a little 1 next to all of these numbers. So this 1 means we're going to take one of these from the s orbital and one of these from the p orbital. So an sp orbital is going to look like this, where we're going to have 2 of those. And then we notice that we have 2 left over for the other p orbital, so we can add p, and we have 2 left, because this is 2 unpaired p orbital, 2 unpaired groups of electrons in the p orbital. So now I'm going to do something like sp2. Go ahead and write that out. Okay, so again, imagine a little 1 next to your s, because s will always be 1. That's really important to remember. So we have a 2 on p this time. So let's go ahead and write out sp2 right here. Excuse me. sp2. 2. Perfect. So we still want to take our 1 from the s, but now this 2 is saying take 2 from the p orbital. So we're going to take these 2, or really any 2. It doesn't matter for our situation here. So now we have 1, 2, 3. So sp2 is going to be 1, 2, 3. Perfect. 3 things. It's going to be important later. And then we notice, oh no, we have 1 left over. So we're just going to have 1 pair unbound, or ungrouped with the rest of these, as just p. sp3 is going to be very similar. P has 3, s has 1, so it's going to be all 4, and you're going to have nothing extra. Let's get into what happens if we start involving d. So let me just erase a lot of this. Now I'm going to go and we're going to do sp3d. And we're also going to do sp3d2. Hopefully you can see where this is going. Imagine a 1 right here, a 1 right here, and a 1 right here. So we want to take 1 from the s, i.e. this. We're going to take 3 from the p, these 3, and we'll take 1 from the d. So we're going to go ahead and we're going to write sp3d. And we have 1, 2, 3, 4, 5. So we're going to do 1, 2, 3, 4, 5. And then how many does our d have left over? It has 4. So we're going to add plus d, 1, 2, 3, 4. Perfect. This one, very similar. We can see that we have 1 from the s, 3 from the p, just like the last one. But this time, we're taking 2 from the d. So we're going to do sp3d2. And then we're going to notice that it's 1, 2, 3, 4, 5, 6 this time. 2, 3, 4, 5, 6. And then how many does it have left? We have 3 that we didn't add, so we're going to do D, and we're going to do 1, 2, 3. Perfect. That pattern is going to follow. This can go all the way up to sp3d5, which is going to be more or less, if I just erase this, it's just going to be that instead. Because we can see we have S1, and we have our 3 Ps, and we have 1, 2, 3, 4, 5 Ds. Are you going to see this very often? Probably not. But that's how you know. Now, there were also some problems on the handout we got that asked you to be able to find whether or not, or that asked you to be able to find this based upon a given atom that you have with a Lewis structure. So I'm just going to go ahead and erase this really quick. And then we can go ahead and get started on how to find the individual hybridization bonds of atoms in a molecule. It's actually much easier than you think, or at least I hope it is. If not, this video should help make it easy. So I'm going to go ahead and pick out a molecule. And by pick out a molecule, I mean I already chose a molecule. We're going to do acetaldehyde. Very hard to say. So we want to go ahead and draw the Lewis structure of it. We know that we have a carbon right here, carbon. We have 1, 2, 3 hydrogens around it. We have a carbon right here. we have an oxygen that is double bound, and we have an H. You can also write this as CH3CHO or COH. I don't remember the order that you're supposed to write them in. But what's important about that is nothing. We don't need to talk about that. Let's go ahead and talk about how we can find the actual hybridization of any one of these given bonds. So we want to go ahead and first make sure that we have all of our valence electrons covered. This has 1, 2, 3, 4 bonds, 2 each. This one's full. This one has 1, 2, 3, 4 bonds. This one's full. This oxygen has 4 electrons on it because there's a double bond right there. And we want to fill that octet. So important that you draw your valence electrons. The most important step in finding which hybridization shell you're in is drawing your Lewis structure. So that's really going to help. So let's go ahead and find the hybridization of this right here. So the first thing that you want to do is you want to count the number of things surrounding the atom. In this case, we have 1, because a double bond only counts as one thing. 2, so I'm just going to write our little numbers. We have 1, 2, 3, and we have no lone pairs of electrons. So what we want to do is we want to look at the steric number. The steric number is another way of saying things. So in this case, we have 1, 2, 3 things around it. So we want to go down to steric number 3. Perfect. How many atoms bonded do we have? We have 1 carbon, 1 hydrogen, 1 oxygen. And this is to follow the chart. And this is following the chart from the left. You can also follow it from the right if you want. So what you want to do is we have 3 atoms, 0 lone pairs. That means our geometry on this is going to be trigonal planar. So I'm just going to write triplane. And because it has 1, 2, 3, let's go back up to here and let's look at our S and P. We have 1, 2, 3, which means this should be sp2 if we follow this all the way over with 3, 0, trigonal planar. Would you look at that? It's sp2. Now you can see that this is going to be extremely helpful later down the line. Okay, so for our next molecule, we're going to use another one that I've already chosen. We're going to use this one. So let me just drag this down here for a minute. So I mentioned earlier that there's a bit of a shortcut that we can use to figure out what kind of orbital hybridization something has. We're going to put that into play here. So I'm going to start by using this carbon atom right here. So if we look at this carbon atom, let's look at how many things it has. It has 1 bond, 2 bond, and then a double bond. It's important to note that a double bond and a triple bond still only count as one thing. So in this case, this carbon atom has 3 things and 0 lone pairs because those 4 pairs take up 8 electrons. So we can see that we have a 3, 0. So if we go to our steric number 3, number of bonded atoms, 3, number of lone pairs, 0, trigonal planar, 120-degree bond angle, we have sp2 hybridization. Now, there's a little bit of a faster way that we can figure that out without having to remember this chart. If I go ahead and write out sp2 like this, earlier I said you can imagine a little 1 in the corner of these. What you can do is you can find the number of things you have. So for example, if this was like a 2, 1, the number would still add up to 3. We can see that if we take our 1 in front of our S and our 2 in front of our P, we also get 3. So I can see that something that has 3 things is going to have an sp2 hybridization. Now, this also applies to other atoms in the molecule. For example, let's look at this carbon down here at the bottom. This carbon has 1, 2, 3, 4 things bonded to it. And it has 0 lone pairs of electrons because it has those 4 bonds that take up 8 of them. So we're going to look for steric number 4. But that's what we would normally do. Because we know that we have 4, what can we add 1 to? Because we're always going to have S in our hybridized orbital. To get 4, we can add 3. So we know that this is actually going to be sp3 because there's a little 1 right there. And if I follow over 4 atoms, 0 lone pairs, we have sp3, which is really nice. Now, if we move into something with, say, d orbitals, which nothing in this atom is going to have something with a d orbital inside of it, we can go ahead and look at, say, something like, let's do sulfur hexafluoride. A sulfur hexafluoride is a sulfur in the middle, and you have 6 fluorines coming off of it. So let me just draw those. 4, 5, and 6. This sulfur has an expanded octet, so this actually has 12 electrons around it. Because it's only the elements in those first 2 rows of the periodic table that have to adhere to that octet rule. They can be expanded past that. Something I want to mention about expanded octets in our case is the elements that we're going to see with those expanded octets most often are going to be at the very end of that 3rd period or that 3rd row on the periodic table, the silicon, phosphorus, sulfur, and chlorine. Something like fluorine or carbon is not going to have that expanded octet because it's only in the 2nd row as opposed to the 3rd one. So if we go ahead and look around this, we see that we have 1, 2, 3, 4, 5, 6 pairs, or not 6 pairs, 6 things bonded to it. Now we know that we have 6 of those and we have 0 lone pairs. Without even looking, I can tell you that this is going to be D2sp3. Because if I go ahead and write that out, D2s1, because S always has a 1 there, P3, we can see that 2 plus 1 plus 3 is equal to 6. So I could see this immediately, count all of the things it has, and say it has D2sp3. Likewise, let's say if, for whatever reason, this only had 5 fluorines around it, are you going to see something like this? Not as often as sulfur hexafluoride, but I can look at this and count 1, 2, 3, 4, 5. Let's say it doesn't have a lone pair in this case. We know that it's going to be a DsP3, making sure to put a 1 on the D because we only have 5 things, and 1 plus 1 plus 3 is equal to 5. And you can actually see if we look over at this chart, if we have 6 bonded atoms and 0 lone pairs, like we do right here, we follow it over. We have sulfur hexafluoride as our example, and we also have D2sp3. And some of these are actually really good examples that they give in this chart. For example, SF4, which is going to look like this. 1, 2, 3, 4. We see that there's 1, 2, 3, 4 things, so we might think, oh, sp3. But we also have to have a lone pair of electrons there to make our 5th thing, so that we know that this was actually going to be dsp3, much like it would suggest over there. If you have any other questions, feel free to leave them in the comments. You can also feel free to ask me in class. But with that being said, I think that's everything that I have for you today.